But you also said that the trajectory of the satellite, it's around the equator.
Yeah.
And if you look at the geographical distribution, I mean, probably it's not by chance that the peak is around center.
No. Yeah. That's so what I was stressing here was not just the peak, but it was actually the peak of TGF distribution is here. I was stressing this feature that this feature about this sharp cut. Why that? Okay, this sharp cut here, and of course we have many satellites, but what we see is that this image is done with different satellites. So the edgeless satellite is the red one, and we have a quasi-equatorial orbit, so of course the exposure is over the tropics. But if you deal also with RESI, which is 38 degrees, now here you cannot see that, but if you plot the distribution weighted for the exposure time, okay, and the scanned region, you see that they are actually clustering over the same regions here. So maybe this plot is not so effective, but there is an increase here of events. You see here they're more sporadic. Of course, the exposure time is less, but in the calculation you take into account this. Okay. Because that's a good point.
Any question? Okay, so thanks again, Alessandro. Next speaker is Alessia Nicosia. It talks about heterogeneous nucleation of ice in the atmosphere.
Good morning, everybody. My name is Alessia, and my speech is about the formation of ice crystals in clouds. And the main actor, however, of my presentation are a specific class of aerosol particle who is able to trigger the formation of ice. For this reason, we are speaking about heterogeneous nucleation. So just a few words about aerosol, who they are and why they are so important. For the many of you who don't know, aerosol particles are solid or liquid particles suspended in air, and their dimension go from a few nanometer to about 100 micron. Beyond this limit, we have gravitational sedimentation, and the resident time for this particle is not big enough for us to have an interest in them. But where this particle came from? We can distinguish between natural emission or anthropogenic emission. Example of natural emission are like volcanic emission or sea spray from the ocean, and some example of anthropogenic emission, but you know pretty well, traffic, industrial activities, also agricultural activities. And because this particle remain quite long in the troposphere, they can interact with each other and also create new particle that we call the secondary phase. However, I don't know if you are aware, but aerosol particle have a big create a big concern for us, and the World Health Organization has said in his report that outdoor air pollution is related to premature death. And however, here in Europe, we are pretty lucky because we have a very capillary network of monitoring stations, and we measure constantly the concentration and chemical characterization and size of aerosol particle. And we have clouds who are really effective in removing the pollution created by this aerosol particle. And we have a strong interaction between aerosol and clouds. Aerosol trigger the formation of both liquid droplet and ice crystals. And ice crystals can then grow and create the beautiful snowflake. Here you can have some images. However, what I'm focusing on is just the so-called primary formation of ice. And to have the formation of ice in clouds, you can have either just the transition between pure water into an ice crystal, but in clouds these necessitate temperature below minus 38 degrees. And this is not the main mechanism. This is called homogeneous freezing. The mechanism that play an important role in clouds are heterogeneous mechanisms. So we mainly need aerosol for the activation of the ice crystals. And aerosol provide a substrate which is able to lower the energy barrier necessary to activate the formation of ice. And we need to, however, differentiate between 4 different activation mechanisms. The direct transition between vapor phase and solid phase on the surface of our aerosol particle, and we call this mechanism deposition. Or the intermediate step with, on the liquid phase. And here we need, however, to distinguish between the case in which we have a liquid droplet with inside our aerosol particle, or the case in which we have the formation of a liquid film on the aerosol particle, or the case in which, by chance, our aerosol particle in black impact a liquid droplet. And in this case, we have the passage between the liquid phase and the solid phase, but the intermediation of our aerosol particle. And here we have the result of some preliminary study made after the 50s. And what researcher has seen is that not all the aerosol particles are able to induce the formation of ice crystal. Just a small subset of the aerosol particle in the troposphere have this ability, and we call this small subset of aerosol particle the ENP particle, ice nuclei particle. And the capability of ENP to induce ice formation, however, depends on the specific mechanism that you are studying, like, for example, the direct transition between vapor and solid phase. You need to take into consideration temperature. The more you go down into temperature, the more you can have the production of ice crystals. And however, one of the parameterization that is often used now into cloud models is the one of Meyer. And this parameterization doesn't take into account the specificity of aerosol particle. She just says we know that we have a small subset of atmospheric aerosol particle able to induce ice formation, and we know that they can be activated more easily going down into temperature. Actually, you should know that just about one particle every 1 million of atmospheric particle is able to induce ice formation. So they are really rare. And however, we want to know why they have this capability and the other not. One hypothesis is that on their surface, the ENP particle have some active site in which the crystallographic structure remember the structure of ice crystals. And this, however, is an hypothesis on why they are able to activate the formation of ice crystals. This is a little bit of a state of art of the studies made in the last 10 years. Here we report just the data taken from the immersion freezing, which is just one of the 4 mechanisms I showed you before. And normally what we are doing now is trying to see really the specific activity of target particle and trying to understand what are the main sources of ENP population. And mineral dust particle are really good ENP particle. And to classify the nucleation, the ice nucleation capability of a particle, we have several parameters. Here I have reported in the epsilon axis just one parameter, the surface area activation rate. However, you should just consider that the bigger is this parameter, the better is your ice nuclei particle in forming ice crystals. And as you can see, is a little bit of a mess. We need to take into consideration several parameters, not only the fixed mechanism, but also the region of activation. Normally what is done is vary the temperature and the supersaturation level, which is a parameter giving you the amount of water vapor and the tendency of water vapor to change phase, and we try to find the region of complexity of this problem. Other critical aspect of this study is that we have several measurement techniques, but no instrument is able to activate the 4 mechanisms at the same time. We can study just one mechanism at a time. And the majority of data that we have belong to ground-based measurement, and they are not completely representative of what happens inside clouds. In clouds, we can have effect like the coating of this particle, and the coating can deactivate their capability to induce ice formation. However, what we really need now is to understand if the ENP population has a major contribution in the natural or in the anthropogenic emission, and provide simple parameterization to model or represent clouds. Here I show you just an example of a real-time measurement technique called the continuous flow diffusion chamber. This real-time measurement technique has one big limit. We can just measure particles smaller than 3 micron. So with this technique that is, however, used pretty much, you can just study all the population of the AIDA facility that is a facility really important for people studying atmospheric physics and clouds. And I found really interesting the fact that it was a nuclear reactor that was converted to the study of atmosphere, and since a few years is operative in Karlsruhe. However, to go directly to the technique that I'm using in ISAC laboratory is a technique based on a filter, on the filter processing. We just sample aerosol in a filter and take them to the lab. And at the laboratory of ISAC, we have a small cold chamber in which we can activate the ENP particle that are collected on our filter. So the filter processing technique is used also by other groups in Europe, but the specificity of ISAC laboratory is the use of this cold chamber, the dynamic filter processing chamber. It's a very easy instrument. We just have a pneumatic circuit in which we let the air flow in a closed loop, and first the air spread inside this granular bed of minced ice. Just to let you understand better, it's like a sort of granita without any flavor. So the air spread inside the ice and take the vapor, the water vapor of the ice. And when it became supersaturated, we let the air enter in this second section, in which we put the filter, and the filter is in contact with the Peltier. So we can vary the temperature of the particle that are gathered on the filter and the supersaturation level. And we can find the activation region for the particles that are collected on the filter. And what you obtain at the end is just these white dots on your black background. And these are our ice crystals, and you can count them with any image analysis technique. I have personally used MATLAB imaging toolbox to make this analysis. So we have the number of ice crystals that are grown on our filter on a certain condition, and we need, however, to calculate the ratio considering the total amount of particles that were collected on our filter. And to do so, we can use either the information of an optical particle counter or a scanning mobility particle sizer, depending on the size of the particle that you want to take into account on your study. The optical particle counter normally is preferred because you can transport it very easy. However, you don't have the information of the concentration of particle below, let's say, 0.3 micron. In this year, we focus on the study of the ice nucleation capability of on the ice nucleation capabilities of cellulose particle. There are some speculation saying that the disintegration of leaves can bring cellulose particle, can release a cellulose particle that can interact with clouds. And in our laboratory, we have the instrument able to generate aerosol particles starting from cellulose powder, and we collect our particle of cellulose on a filter, and we analyze their ice nucleation capabilities in our chamber. And in this video, you can see what happens when we analyze the filter. It takes a little bit of a time. We don't have an instantaneous growing of ice crystals. However, we have studied that for cellulose particle smaller than 0.4 micron, we don't have any contribution for the growing of ice crystals. And another application of our instrument in Isaac Laboratory is the study of the atmospheric concentration of ENP in a certain location. Here I'm showing you the result of a measurement campaign in San Pietro Capofiume. And normally what we do is distinguish between the contribution of PM1 and PM10 aerosol particles. So we collect aerosol particle in two different filters, and we use an impactor to distinguish their size. And also we collect the information of the wind direction, because the wind direction can allow us to make a study of back trajectory of wind, and we can sometimes relate our EMP concentration to phenomena like Sahara dust transport. However, just to conclude, because I think we are a little bit there are different implications in the study of the properties of ENP particle. First of all, it's important to understand better the formation of ice crystals, and ice crystals in clouds are related to precipitation formation, especially at our latitude. And the properties of ENP particles are also related to the interaction of aerosol and clouds. And this is important also for a global climate model. Here you have a pretty old graph of the International Panel of Climate Change, reporting that one of the major error bar for the model are the our description of clouds and how they interact with aerosol. And just to trigger more your interest in this subject, I have reported some European projects that were financed and in which a part of the researcher were expert in this field, in the field of ENP particle. For example, Ben Murray of the University of Leeds spent a lot of time studying the properties of ENP particle, and then he was able to win an ERC project, and he found his own startup trying to improve the storage of biological sample at low temperature. However, this is not my field of expertise now, so it's just for your curiosity. There are also people working together with material science, expert of freeze-drying technique. And as you probably know better than me, freeze-drying technique allow the formation of ceramic material with controlled porosity. And you let the ice grow on like hydrogel, and then you sublimate the ice and you take it away, and at the end you have a controlled porosity inside your material. And being able to control the initial formation of ice is important in this technique. And as said by my colleague before, the study of cloud is also important for enhancing aircraft safety. So thank you for your attention. And
are there any questions?
I like I was working before, in the bachelor in atmosphere, transfer radiation in atmosphere. So my question related with the plot that you show about ice nuclei particles concentration versus temperature. This is how is built this plot. I would like to know, all of the details of this plot. Because
you mean this one?
Yeah.
Here you have data coming from different groups in Europe and also in the world, in particular studying immersion freezing. So just the case in which you have a liquid droplet with your aerosol particle inside, and imagine that you have just mineral particle, like Arizona test dust. You put your particle inside a very small liquid droplet, and you see the activation rate, especially by lowering down the temperature. What I found really, but I go a little bit too fast on this graph. However, we know that bacteria can have a role as ENP particle. And there are a lot of speculation on this fact, saying that probably bacteria use this capability to be transported far away. And however, because this is not just important, the fact that the particle is able to activate ice, but also how many particles you need to have enough ice crystal to have an effect. We know that bacteria are able to be activated at low temperature, minus 10 degrees, but you need a very big amount of concentration of bacteria to have an effect. They are a little bit poor ENP particle, considering the activation rate. A mineral dust particle that can be activated at normally minus 22 degrees are better ENP nucleator. You need less concentration of mineral dust particle to have an effect. And what I found really interesting is that we have phenomena of transport of particles from the Sahara. And in general, you have a lot of, in every part of the world, you have the transport of particles coming from desertic area. And these particles are the best ice nucleator. So particles coming from the desert who have not seen water, when they are in clouds, in contact with water droplet, they are the one who are able to initiate ice. And who probably has this crystallographic structure, remembering the crystal structure of ice, is something I found.
My question goes thinking, there are some studies in the atmosphere of the exoplanets. So there are some studies of the atmospheres of the exoplanets. Exoplanets, the planets that are found in other stellar systems. So I was thinking that we can decumulate. I mean, we can go to the thing that we can see in the atmospheres and later try to see if there is some particles. I mean, because there are the bacteria component there, and this is astrobiology thing. So
no, but apart from exoplanet, I know that in the AIDA facilities they are doing experiment trying to study the atmosphere of Mars. So clearly we use what we know here, trying to understand also what happened in other planets.
Other questions? Okay. We can thank again Alessia. Okay, next speaker is Davide Putero. His talk is about Staflux, a tool for investigating stratospheric intrusions.
Okay, good morning everyone. Today we'll talk about ST-Flux, which is a tool for investigating stratospheric intrusions, and I will show its application in a crucial area for this phenomenon of stratospheric intrusions, which are the Himalayas. I'd like to say that this study has been done in collaboration with the Institute of Atmospheric Climate and Science of the ETH in Zurich. I'd like to start with some definitions, as already presented by Alessandro before. This is the Earth atmosphere. In this talk, we will focus on the two lowest layers of the atmosphere, which are the troposphere and the stratosphere, which are characterized, as you can see in the picture, by very different conditions, such as the temperature profiles or some chemical constituents concentration. For example, in the stratosphere, the ozone has its maximum, and here it has a beneficial effect since it protects us from the incoming ultraviolet radiation, while in the troposphere, the ozone is one of the most harmful pollutants because it's one of the most important greenhouse gases. The boundary between these two layers is called tropopause, and it's not a hard boundary, since some exchange may occur between the two layers. And here they're represented. You can see with this like pink-brown color the troposphere. The yellow and blue indicate the stratosphere, and this thick black line indicates the tropopause. As you can see, all these green arrows indicate some exchange that may occur because of natural processes, and they have impacts on the meteorology, atmospheric chemistry, and climate change. In this talk, I will focus on the stratospheric intrusions, like indicated by this red arrow, which are the downward transport of stratospheric air masses relatively deep into the troposphere. And sometimes they can also reach this brown layer, which is the planetary boundary layer in the troposphere. The stratospheric intrusions are a topic of ongoing research because of several reasons, such as the where and how often they take place, whether there are any long-term variation, the quantification of their contribution to the ozone levels in the troposphere. And this is important because some modeling studies have indicated that the stratospheric contribution to the tropospheric ozone could be as large as that from net photochemical production. But even there are still some large uncertainties in these estimates. And then also by deploying measurements in high mountain sites, we observed that there's a significant contribution of the ozone in the troposphere due to these events. Also, it's important for attributing long-term variation and see what's the efficiency of some precursor emission reduction. The purpose of the tool ST-Flux is then to obtain a fast computing, relatively user-friendly, and reliable identification of the stratospheric intrusion that occur at some place on Earth and during a selected time window. It is based on a compiled stratosphere to troposphere exchange, STE climatology, which then can extend calculation back to 1979, and this is especially important because in some areas of the world we don't have any measurements available, so it's important for assessing a climatological assessment of the stratospheric intrusions. And then it's also important because of investigating their influence on the ozone levels and attributing an eventual long-term variability. This is the input database, this climatology I was talking about, which was developed by Skerlach et al., and it's currently available and currently updated at the ETH in Zurich. Basically, every day set of global trajectories is calculated. You can observe all of them here, and these are based on the input wind fields deriving from the INRiM reanalysis dataset from the CMWF. Among all of these trajectories, only those who cross the tropopause in the first 24 hours are retained and extended backward and forward in time. Then we can obtain 9 days long trajectories that come from the stratosphere. And then a 3D labeling algorithm is applied to indicate points of stratospheric, tropospheric nature or eventual anomalies. With these trajectories, the ST-Flux tool checks all of the trajectories that go into a box which is defined by the user by its horizontal spatial coordinates and the vertical top lid of the box, and obviously during a selected time window. So each day, ST-Flux counts the number of trajectories crossing the box and gives several output files which enclose the position and time of the crossing, position and time of the first crossing each day. Also, this is important, the position and crossing of the tropopause, so for each trajectory, and the entire list of the trajectories. And in the picture, this schematic picture, you can observe an application of ST-Flux in the region I will consider in this study, which is the southern Himalayas. Obviously, we obtained a time series of days possibly affected or not by stratospheric intrusions according to this methodology, but we had to test it against another methodology which is based on some experimental data. In particular, I was talking about the Himalayas, and this methodology called Stratospheric Intrusions Observations, abbreviated SIO, is based on the variation of several parameters, among which some are collected at this station, which is the Nepal Climate Observatory Pyramid, NCOP. It's one of the 31 global stations of the Global Atmosphere Watch program of the World Meteorological Organization, and it's a remote site placed in the southern side of Mount Everest at 5,079 meters above sea level. So it's a site often affected by stratospheric intrusions. And here, by some colleagues of mine, in 2010 it was developed a methodology based on the variation of some measured parameters such as relative humidity, pressure, ozone values at the station, some satellite observations such as the total column of ozone in this area, or other modeling products such as the potential vorticity values calculated along back trajectories that arrive at the station. So by applying all of this, we obtain a time series of days possibly affected or not by stratospheric intrusions. And here in the plot you observe the daily average ozone values collected at NCOP, and in red each day is selected or not by this methodology. Obviously, applying ST-Flux we obtain a similar data set And our ST flux configuration was the following. We built a 3 degree by 3 degree box around NCOP location with a vertical top lid of 550 hectopascal over the same time period. And here I show the comparison between the two methodologies. The agreement between these two time series is not due to chance because it's statistically significant when comparing the events at 99% confidence level. And it has to be said that ST flux where represents the annual cycle. Here you observe the annual cycle calculated with ST flux, and here the one calculated by deploying observations. We have a maximum of stratospheric intrusions in the winter months and a minimum in the summer months, which correspond to the Asian monsoon. Similarly, also the interannual variability is kind of well represented. Here we have the frequency of stratospheric intrusions, seasonal value, for the two methodologies, and we observe that more or less the peaks are well represented. There are still some differences between the two, like here for what concerns the amplitude of the peaks or sometimes the timing, and these are due to some strong and weak points of one methodology with respect to the other one. For example, ST flux is based on the grid deriving from the INRiM reanalysis, so it's not fully able to capture these subgrid scale processes such as convection, turbulent diffusion, mixing, and this can be an explanation of the disagreement between the two. In contrast, the observations might not be able, in case of long travel times, obviously, to detect the stronger impact of mixing and dilution on the air masses that arrive at the station. And if we observe what's the delta T, this parameter is simply the difference in hours between the tropopause crossing and the box crossing. What's this average delta T? We observe that at NCOP we often observe this long travel time, so this can be a cause for the mismatch between the two. Lastly, there's this overpasses phenomenon, which is air masses that overpass the station at altitude so high that there's no track in the measurement record. So these are strong and weak points of both methodologies that we should keep in mind. And by keeping these in mind, we exploited another feature of ST flux, which extend calculations back to 1979. And then we obtained a long-term evaluation of the stratospheric intrusions for NCOP. So over this 35 years period, we observed 673 events, which correspond to 13% of the period. And also we recalculated the seasonal cycle. It's well represented. We have the same feature as before with the minimum in summer and maximum in the winter months. Then we can obtain also lots of other useful plots, such as the density plots for what concerns the tropopause crossing locations. Here we observe that these are all the tropopause crossing location associated to the trajectories coming into the box with the same configuration as before, except for the time period. And we observe that we have two preferred regions for tropopause crossing, which correspond to the Central Asia and the northeastern Africa, close to the Mediterranean Sea. And these two are in lines with some previous works which indicate these two regions as kind of preferred for the occurrence of tropopause crossing. Then we obtained a time series of monthly SI frequency in percentage, and we checked for eventual trends in this signal, and no trend is observed except for winter seasons, in which we observe a really slightly positive trend. Furthermore, we applied a complete ensemble empirical mode decomposition with adaptive noise, which is a quite long name, for this decomposition technique, which decomposes the original signal into several so-called intrinsic mode functions, IMF. Each of one is characterized by a different period, so it might indicate a potential oscillation in the original signal. And the sum of all of these IMF plus a residual, which indicates the trend, gives the original signal. So we decomposed our original time series. We obtained a first IMF with a period of 1 year. This was quite obvious because we observed before that this is a characteristic period. Then we had another one with a clear period of 28 months, and we tried to relate this to climatic factor, which is the quasi-biennial oscillation. In the plot, this is indicated by the blue line. It's an index which indicates the positive and negative phase of this quasi-biennial oscillation, which is a global change in the tropical winds in the tropical winds of the stratosphere, and which in previous studies it has been observed to be anti-correlated with some stratosphere to troposphere exchange, and it's the same that we observe here. We observed several periods of inverse relation between the two. Then we had another IMF of period of 3.5 and 5.8 years. We tried to relate this to El Niño Southern Oscillation, which is another climatic variation with a irregular period of nearly 4 years. And we observed that in some cases we have not anti-correlation but inverse relation between the two signals. And lastly, we had our last IMF with a clear period of 10 years, and this was possibly related to the solar activity. So in conclusion, I presented STE flux, which is a tool to represent the stratospheric intrusions occurrence, and it's really powerful, especially for representing the seasonal cycle. And the agreement with the time series derived by the observation was not due to chance. This tool can be used, of course, in combination with observational data sets or deployed in areas where we can't perform any measurements. Then, by exploiting a feature deriving from the INRiM analysis dataset, it can allow for a climatological analysis from 1979, and we observed that the intrusions affected NCOP for 13% of the period, although no trends were observed. And then by applying the SIMDEN analysis, we show possible influence of several climatic factors. If anyone is interested in the ST flux outputs, may write to me and we can arrange some calculations. And I also would like to say that there's currently a paper in review in atmospheric chemistry and physics discussion about all these results that I presented today. So thank you for your attention.
Are there any questions?
Thanks for your talk. As far as I know, also thunderstorms may play a role in the production of ozone and closing the electric circuit. So
Sure.
I've seen many distributions. You tried to compare the distributions. Did you try also to compare it with the lining rate? Okay.
No, so far we...
Because I've seen that with the solar cycle, so there is some
yeah.
evidences of...
Yeah, with this one. Yeah, we simply... we didn't take into account the lightning activity, but yeah, it's something with it.
Maybe it's a suggestion.
Because this last part is actually under study. I mean, understanding what's the correlation between these climatic factors and our IMF is currently under study.
I guess also thunderstorms go in the stratosphere. You have this intrusion. So okay, thank you.
Other questions?
Davide, did you think about the possibility to use meteorological forcings from models, for global climate models for the future conditions to make likely projections of future stratospheric intrusions, the same way as you use the reanalysis for the past?
No, currently not, but it's something that's maybe very useful, especially because models can go even at a deeper resolution, so it can help also for reanalyzing the past.
Other questions? Okay, no? Okay, let's thanks again, Davide. Okay, now it's a very pleasure for us to host Elisa Palazzi from Institute of Atmospheric Science and Climate in the National Research Council. And her talk is about climate change in the mountains.
Okay, thank you very much for the invitation to this interesting conference. So this is quite a different topic with some links with the previous talk, because I will talk about almost the same region to give an overview of this general topic related to climate changes in the mountains, which is what I'm doing since some years here in Torino. Mountains, why are we studying mountains? Because mountains are very special and very important environments. Mountains exist in many regions of the world. They are home to a significant fraction of the world population and to almost half of the biodiversity hotspots. Biodiversity is something that we do not consider often, but biodiversity is a very important service that our climate system naturally provides. Biodiversity is at the basis of the evolution and a product of the evolution itself. So some people now think that we are going towards the 6th extinction, like the other 5 that occurred in the history of the Earth, exactly because of the loss of biodiversity, essentially due to the anthropogenic impact on climate and environment. Mountains make essential ecosystem services available. First of all, water. Mountains are called the water towers for the Earth because they provide fresh water to billions of people, and which is used for domestic use, irrigation, hydropower industry. Mountains host unique flora and fauna and critical habitat for species, different species. Provide wood, provide recreation, snow-based recreation, so it's important also for touristic reasons. And the important role of mountain regions has been highlighted also in the framework of many international programs and initiatives. For example, in 1992, at the Rio de Janeiro Earth Summit, as in the chapter 13 of Agenda 21, where mountains' role has been confirmed. So for sustainable development in mountain regions, giving mountains crucial role as sources of water, energy, biodiversity, forest products and agricultural products, and so on and so forth. In 2008, for example, in the General Assembly of the United Nations, where the key role of mountains has been recognized, especially looking at their very, role as sentinels of change, especially in terms of vulnerable resources like biodiversity and water. So why do we care about mountains? Exactly because mountains are so special environments, but at the same time, they are very fragile environments. They are among the regions that are most sensitive to climate and to environmental changes, and where the impact of human activities may have a very important role. So changes in climatic variables such as precipitation, snow, temperature, wind, and circulation patterns, and all associated effects may have an important role for future water availability, for the cryosphere system, for biodiversity, for the ecosystem, and for the provision of ecosystem services like water, for example. So, in this study, in this talk, I just show you some examples of study of mountain climates, taking probably one of the most important mountain regions of the world, which is called the third pole of the Earth, the Himalayas, Karakorum, Pamir Mountains, the Tibetan Plateau. The third pole because this region here hosts the largest reservoir of snow and ice after polar regions, and because the main river systems in Asia originate from these mountains here, and rivers are fed by snow and ice melt and by precipitation, of course, which is brought in this region by 2 main circulation systems. The most known is probably the monsoon circulation, the monsoon systems that system that brings precipitation from June to September, climatologically speaking, and especially in the eastern part of this area, in the eastern Himalayas. But the western part is also affected by another system, westerly winds coming exactly from the North Atlantic region, from the Mediterranean regions. So in this area, in the Mediterranean, in the Atlantic, there are some winds that flow toward Europe too, affecting weather and climate in our regions, but also in the Karakoram area, so the western part of the Himalayas, such that, for example, winter precipitation in the Karakoram has larger values according to specific phenomena that occur in the Atlantic. These are called teleconnection. So areas that are far from each other in the world are in a way connected through winds and through waves in the climate system. Our understanding of these the climatic processes occurring in the mountain regions like the third pole is, however, still incomplete because of the difficulty of measuring climatic variables in so harsh environment, and also because of difficulties in modeling these phenomena and these processes. So both observations and models are quite uncertain in the mountain regions. I will talk especially about three main topics that are related to climate mountains, and in particular the first one, which is called elevation-dependent warming. It's the tendency of warming rates to be amplified with the elevation. So you probably know that we have had a strong warming in the last century, more or less globally, over the whole globe. But in the mountains, we have more and more rapid warming than elsewhere, than in the lower lying region, than compared to the global mean. Because mountains are exactly, as I was saying, sentinels of change. Mountains answer more intensely to possible changes with more severe and more negative, in a way, consequences. I will also talk about changes in precipitation and in snow, especially snow at ground, which are, of course, related to the first topic I'm going to discuss with you. So elevation-dependent warming. Of course, the fact that mountains are warming more than other regions have important implications for the high-altitude cryosphere system, for glacier dynamics. Think about the possibility of glacier to retreat, as has happened over the last decades, almost everywhere in the world. And of course, for the provision and availability and distribution of water. So this is a very important phenomenon to be better understood and measured and modeled, because it's really important also for a sociological point of view. It is not very easy to study elevation-dependent warming because difficulties arise from the sparseness or even the lack of long-term in situ observations. Because when you want to detect elevation-dependent warming, you have to first detect a warming. And this means having into disposition a long-term data set, so many years, because otherwise you cannot assess any climatic trends if you have a few years of measurements. And these measurements have to be located at higher elevations, because you have to measure what is happening in the mountains, even at the very high elevations, above 5,000 meters, let's say. There is also a lack of consistency in the methods that are used so far to quantify elevation-dependent warming. And especially, enhanced warming is usually occurring in response to many climate variables that are all interconnected with each other, giving rise to complex feedback mechanisms. So it's not very easy to study this phenomenon because it is a complex one, as most phenomena occurring in the climate system. This is the region of study, as mentioned before, and this is the almost real topography of the area from a very high resolution digital elevation model. And this is the data set I've used in this study to assess elevation-dependent warming. I will not deal with measurements in this study. but models, and in particular the global climate models of the latest IPCC assessment report. I don't know if you are aware about that, the Intergovernmental Panel on Climate Change, which publishes every 7 years more or less a report on the state of climate and on the causes of climate, so attribution experiments and so on and so forth. And this is a subset of the model ensemble of the models that are used by the IPCC. Okay, so these models are very different with each other, and in particular they have very different spatial resolutions. Of course, in this case, when I want to study mountains that are very heterogeneous environments, the resolution is an important characteristic of the model. So the higher the resolution, the higher is, at least in principle, the skill and the performance of the model in these very rapidly varying environments. This is the orography seen by the average of the model. So I took all these models here whose resolution comes from, ranges from 80 kilometers up to 400 kilometers. So one model pixel can be also 400 square kilometer wide. So it's a very big one. And this is the average of all models at 2 degrees latitude longitude, so more or less 200 square kilometers. And you can clearly see how different are these two pictures. So in general, mountains see, models see a lower elevation than compared to the reality. So the methodology for assessing elevation-dependent warming. As I was saying before, we have to assess some warming. And we exploit the availability of these model simulations that are available for the past, from 1850 to 2005, this is called the historical period of the models, and for the future projections from 2006 up to 2100. And projections have been made under different emission scenarios, so under different assumptions on possible emissions of greenhouse gases in the future or land use changes. I used here the RCP 8.5 scenario, which is the most extreme from the IPCC studies. So I calculated the changes in the temperature between, in the historical period, I would say between 1971-2000 and 1871-1900. So the change between two 30 years long climatologies in the past, while the future temperature changes are evaluated as the changes between two 30 years long climatologies, one at the end of the 21st century and one at the end of the 20th century. So this is a change. A change can be thought of as a trend. So this is a measure of how temperatures have changed in these two very long periods, in the past and in the future. Then I have to link these changes with the elevation. So, for example, this is a map of these changes for the minimum temperature in the future, okay? And I want to link these spatial changes to the elevation of each pixel. This is, again, the multimodal mean of all these models. I also calculated the same thing for each individual model, but just I'm showing you here just the results for the mean of the models. And in order to assess the elevation-dependent warming, I simply calculated the linear correlation between the changes and the elevation, and calculated the slope of this linear regression and its statistical significance. Okay? So if the slope is positive, this means that we have more warming at higher elevations, so elevation-dependent warming. I analyzed separately the minimum and the maximum temperature because different mechanisms can be at play during day and night. So it is important to look at these two variables separately. These are summary plots summarizing these linear correlations between warming trends and the elevation. This is for the historical changes, this for the future changes. Just look at the first row. Blue lines are the minimum temperature changes, red lines the maximum temperature changes. I'm showing here not just the same thing as shown here, but I use the whole model ensemble and just calculated the statistics from this ensemble within each 200-meter wide altitudinal beam. So the solid line is the mean, the gray shading is the standard deviation of all the model ensemble. So the first interesting thing that you can observe here is that the minimum temperatures in every season, the 4 columns are the season, December, January, February, spring, summer and autumn, the minimum temperature warmed more than the maximum temperature. So we have had more warming for nighttime temperatures, for the minimum temperatures. This is the so-called daily asymmetry in warming rates. This is something that almost disappears in the future scenarios. But most interestingly, we can observe that in fact the correlation, the relationship between warming rates and the elevation is far from being linear. So we made the assumption of linear correlation, but it's not linear. And you can observe this very well here for the future simulation in winter. You have at least 2 regimes that can be distinguished with more warming for the regions above a given altitude, more or less 2,000 meters, 1,500 meters, 2,000 meters, than below. So what happens at these altitudes here? To better understand that, we plot the same thing as here, not as a function of the mean elevation of a given beam, but of the mean temperature. But you know that the temperature can be intended as a proxy for the elevation. But plotting in that way, you can see that this shift between the 2 regimes occurs more or less near the 0-degree isotherm, so the freezing level of water. So something that involves the water phase change, the presence-absence of snow, or the snow albedo feedback as an important role for, probably for these mechanisms here. I go back just for saying that this table resumes the value of the linear correlations between the temperature changes and the elevation for the minimum temperature, the maximum temperature in the past, in the future, and for the 4 seasons. So these models, on average, see elevation-dependent warming everywhere in the past and in the future, but especially exacerbated in the future, and in particular, a strong signal of elevation-dependent warming is observed for the minimum temperature in the cold season and for the maximum temperature in the warm seasons. Okay, we want to, since we have models into this position, we want to understand the mechanisms behind this elevation-dependent warming, because in the climate system, you cannot do experiments as you usually do in a laboratory, because it's too complex, it's too variable, and you cannot have a control on the situation. So you use the models like laboratories. You switch on and off certain variables and you see what happens. You make hypotheses and you check for the correctness of these hypotheses. The models provide every variable you want to know, even the coffee sometimes. The models are helpful in this way to really to understand the processes behind the working of the climate system. So we try to analyze other model variables that may be related to enhanced warming with the elevation. These are all the variables that increase the net flux of energy at the surface. For example, the change in albedo. Albedo is simply the fraction between the reflected and the incoming solar radiation. And it is a property of the surfaces, so that snow-covered, ice-covered surfaces have a very high albedo. Oceans have a very low one. Vegetation have a very low one. It depends on the characteristics of the surface. The change in albedo, the change in the near-surface specific humidity, and in the downward long-wave radiation, which are related to the greenhouse effect in a way, because more clouds implies more greenhouse effect if clouds are of certain type. The change in the downward shortwave radiation, and the normalized changes in the 3 last variables here. So the changes relative to a given climatology. Certain studies have demonstrated that the normalized changes are more effective in explaining temperature changes at the surface than the absolute changes. So overall, we have 7 possible variables that can be drivers of elevation-dependent warming. So we set up a methodology to understand if these are actual elevation-dependent warming drivers. To be those, they have to exhibit a dependence on the elevation as the temperature change does. So we have detected a dependence of the temperature changes on the elevation. So if these variables also have a dependence on the elevation, they have the possibility to be drivers of elevation-dependent warming. But the sign of this dependence has also to be consistent with the amplification of warming rates with the elevation. And last but not least, these changes here have to be spatially correlated with the temperature changes, even if we remove the dependence on the elevation, because otherwise, simply the correlation between all these variables and the elevation can arise from the fact that they all are proxies of the elevation itself. So we have to remove the elevation to check if the correlation among these variables still exists. So this is a graphical way to show the correlation between these 7 possible drivers here and the elevation. This is the minimum temperature in winter. So I just use an example to show the results of this methodology, because the minimum temperature in winter is one of the situations in which the elevation-dependent warming was most striking, according to our previous analysis. So, according to this analysis, the reddish color indicate highest correlation, positive ones, the blue negative ones, blank box indicate non-significant correlations. So, from our analysis, the only 3 variables that have a significant correlation with the elevation with the right sign are the change in albedo, the normalized change in the downward long wave radiation, and the normalized change in specific humidity. So we want to check if what is their role, the competition in explaining the enhanced minimum temperature change with the elevation. We set up a multiple linear regression model in which these 3 variables are used as predictors for the prediction of our predictant, the minimum temperature change. We detrend all these predictors and the predictant and altitude detrended in order to check for the third hypothesis, and standardized in order to let these coefficients comparable with each other. 3 predictors give rise to 7 possible regression models, and we want to check what is the best performing models able to reproduce or to explain the minimum temperature change in winter in this case. So again, a colored figure to show the explained variance of these 7 possible models. This bottom part here indicates the variables, albedo, downward long wave radiation, specific humidity, that are switched on or off in our models. So the higher the explained variance, the higher is the performance of the model. But in fact, to be honest, we have to rank the model according to another criterion, the ICAIC criterion, which allows to weight models having different number of predictors, because in principle, one regression model with more predictors have the best, with the highest number of predictors has the best performance. So, the best performing model able to explain the minimum temperature change in winter is the one including the 3 predictors, in fact, with the highest explained variance and the lowest ICAIC value, which is not, how to say, this is not what is occurring in every case. For example, for the maximum temperature in summer or in autumn, that's another model which is the best one. But the first 4 models are all including the change in albedo. So the change in albedo at ground turns out to be the most important predictor for elevation-dependent warming, which is important, and even it is the most important one, even if we consider the other 3 single predictors models. So this means that this should be probably related to the reduction of snow cover at ground triggered by higher temperatures. And because, of course, the surface albedo is primarily dependent in these areas here from the presence or absence of snow. And in fact, in the past, we performed, looking exactly at the same model ensemble, other studies exactly looking at the possible trends in the future and in the past of snow cover and snow depth. And what we found is that the whole area will be subjected, these as future projections, to a strong reduction of snow depth or snow water equivalent, which is one measure for the snow layer thickness. And also looking at the annual cycle of snow depth in two different areas of the region, in the western part affected by western weather patterns, in the eastern part affected by the monsoon, we expect from the present, the solid lines, to the future, the dashed line, a strong reduction in snow depth. So a strong reduction in snow depth is expected for the end of the 21st century in the whole, essentially in the whole area we are looking at. And not only a snow reduction, but also an anticipation of the snow depth maximum from about March, the actual condition, to February. So anticipation of 1 month in the snow depth maximum in this area. This means earlier melting, of course, of snow resources, and also another timing of the river discharge, which is important for the population living there, because they are used now to have water from snow melt and discharge at a given period of the year, while now this period probably will occur earlier. So this is important to adapt to other conditions. And finally, I just wanted to complete the picture, just showing you another study performed over this area looking at precipitation. So far we have seen that we have less snow at ground, more warming, and we also found for the same region that during winter drying conditions are expected, so less precipitation. So less precipitation in winter means less snow falling, less precipitation falling as snow, less precipitation, higher temperatures, and less snow at ground for sure. So all things combine to give this not very positive picture of the situation. For summer, we detected, on the contrary, positive trends of future precipitation. But again, that's something that is occurring worldwide. So yes, we have more intense precipitation, in fact, that sometimes give rise to a positive precipitation trend, but we also have more longer dry period, more longer periods without rain. So when it rains all together. It rains a lot. It rains very intense precipitation. But the periods of dryness are longer and longer. So this is something which is occurring worldwide and is expected to occur also for the future, except that in some regions in Northern Europe. Okay, the last two slides to let you aware of the fact that we are using models, global climate models, but do we trust model projections? Of course, the models can have very high uncertainties because of very different reasons, and in particular in mountains regions and for certain variables like precipitation, for example, or snow, which are very intermittent and very and are undergo very rapid variations in space and in time. And in fact, you probably do not see that there is here a light gray envelope in these lines, and here is a totally mess of gray lines, which are all kinds of annual cycles depicted by the individual models. The two pink and red lines are two observation-based data sets. So this is the annual cycle of precipitation in the Himalaya, and this is the annual cycle of precipitation in the western part, in the Karakoram, from the observations. The models depict, again, here, a unimodal annual cycle like the measurements. The black line is the multimodal mean, so the mean of all models, and it is yes, it has the same shape as the observations, but you have a lot of lines here with very different values of the maximum. In the Karakorum there, we have a lot of different kinds of precipitation annual cycle, which do not resemble to the observed one. And you can see this better here. We have grouped the model into different clusters according to the kinds of precipitation annual cycle reproduced, for example, in the Karakorum region. And you see that there are at least 4 model clusters, and only one of them is closer to the observations. And also in the Himalayas, you have, yes, unimodal precipitation annual cycles, but with different characteristics, and just one is closer to the observations. So we can ask, what are the models that goes into these 2 clusters here, the best performing ones? What are the characteristics, the features inherent in these models? And we have not a definite answer. We have seen that the models belonging to this cluster here have a quite high horizontal resolution. Yes, the models falling in this cluster here are the models that are able to include the indirect effect of sulfate aerosols that have an important role for the monsoon circulation. But the models having this effect also fall in other clusters. So we have not a clear answer to that, and models have to be improved, not only in terms of spatial resolution, but also inclusion of all processes that are just parameterized so far. But the last thing, do we trust in models? Yes and no, but do we trust in observations? Because for these areas here, also observations can have a huge spread. These are the same annual cycles as before, but for different observation-based data sets, based on the interpolation of in situ station data, satellite, reanalysis data. They do not give this exactly the same pictures. So for these areas in particular, when we study climate here, we have to keep in mind that both models and observations have uncertainties, and probably the best way to analyze these things is to use a multi-source approach and be aware of the advantages and disadvantages of each kind of data, and use all we have to try to provide as complete as possible picture of the situation. So this is what I wanted just to say also in the conclusions here. Probably the last one is the most important. The projections of global climate models in mountain areas are affected by large uncertainties, also because, of course, the controls of topography are still not properly represented in the state-of-the-art models, but increasing the resolution is not the only way we have to improve this drawback. Okay, thanks for your attention.
Are there any questions for Elisa?
So if we restrict ourselves on the Himalaya regions, and despite all the difficulties with the initial conditions and uncertainties, which is the time window for, so to speak, completely melting of the ice on snow on this region?
From the study we performed on snow resources at ground, we saw that using these models here, a reduction of 50% of the snow resources in the eastern part, just in the Himalayas, is expected by the end of the 21st century. So not complete melt. But if you, it depends on the region you are looking at, in fact. This is heterogeneity. So yeah, from those studies and other, almost half of the actual resources could disappear by the end of this century, according to these models, of course, with all their uncertainties.
The second part of my question was, as you said, the albedo seems to be the relevant element, in the relevant factor in the evolving situation.
Yes.
And I guess that also if we just consider the albedo reduction, this is an accelerating factor, which means that less snow imply an accelerated.
More warming.
More warming.
Exactly, because this is one of the most important feedback mechanisms in the climate system, a positive one. The climate system has more positive feedbacks than negative, and positive feedbacks destabilize the system. So you have more warming, you have less snow at ground, you have more absorption of solar radiation at ground because you have less snow. More absorption of solar radiation implies more warming, and this cycle reinforces itself. So yes, the snow albedo feedback it's one of the most important elements of the internal climate variability, because we are dealing with different factors affecting climate, external factors like anthropogenic actions, but also like solar forcing, like volcanoes or Milankovitch cycles that impact on the orbital parameters that have an effect on climate. But the climate would vary also without external forcings applied, because it's a complex dynamical system with our internal variability. Feedback mechanisms are one of the most important expressions of the internal climate variability, in fact.
Yeah, my last part of the question is about the calculation themselves. That means just only about the albedo. This is a typical kind of differential equations in which you have the mechanism which is more relevant as far as the albedo decrease and goes down. So is this scenario calculated practically from a mathematical point of view through differential equations or something like that?
The thing closer to what you are mentioning probably is the calculation of so-called climate sensitivity in the climate system. So you alter some important forcing, external forcing or driver. For example, you double the CO2 and you see what is expected temperature change from this forcing, but also considering other feedbacks, mechanisms that can add to this. For example, the snow albedo feedback, cloud feedbacks, and lapse rate feedbacks, and others. So yes, there is an equation, and there are people that are just working on that. So this is a field, a specific field in the climate research, the one of calculating what is the climate sensitivity, so the answer of the climate system to a given forcing, but taking into account also the other feedbacks that may result as a consequence.
Other questions? Okay, no. Let's thank Elise again.
Okay, let's go to the canteen that will stop serving food at 2. So don't run, but still rush a bit.
sì, infatti. Abbiamo saputo questo. Beh, sì. Un po'. Sì. Sì, sì, ma penso che questa sì, sì.
Okay, welcome to everybody to this afternoon session. We are quite late from the program, but we have to start. The first talk is by Catalano Enrico, coming from the University of Piemonte Orientale and the Joseph Stefan Institute of Ljubljana. And the title is Characterization of Psychochemical and Colloidal Properties of Iron Oxide Nanoparticles and Calcium-Doped Core Shell Nanoparticles for Biomedical Application.
Okay. Thank you for the committee that gave me the opportunity to present today this work about an application of medical physics for possible new opportunity of therapy by using iron oxide nanoparticle that usually they are defined like magnetic nanoparticle with different type of chemistry and synthesis of this nanoparticle. The background of my work was recently published in the special issue of this book, and we published it here to the end of October. And this is about the overview of this work, about the general background of nanotechnology and application nanomedicine, the different type of synthesis that we used for the production of iron oxide nanoparticles, and the different type of physicochemical, magnetic, and colloidal property, like characterization, this nanoparticle, and all the confirmation about chemical, and especially about the heating ability of this nanoparticle in the magnetic field. And also part of work just more important for the final application, this nanoparticle was about the in vitro and in vivo biocompatibility of this nanoparticle. Nano, in particular, the background, it was regarding general application nanotechnology that is now very diffused for different, about the use of nanoscale property, to use these nanoparticle for application in, there are different computer science or biochemistry, but especially for nanomedicine, to use like a carrier for drugs or other type of molecule. And in particular, in the range of the framework, it's good for the property because it can be interact with different type of cells and can be used for different type of disease in the biomedicine, in the biomedical application. And in particular, the use of iron oxide nanoparticle for this project is for a different type of uses. It can be used for tumor imaging, like diagnostic, but in particular, this has double action because it can be used like diagnostic, but also with like therapeutic, and so is the field of theranostics. But also it can be used for biochemistry separation, cell sorting, or other type of application in the field of medical physics or biomedicine. Because the purpose of the project we developed in collaboration with Joseph Stefan Institute, also with Polytechnic of Turin, is to develop a new smart drug delivery to release like chemotherapeutics, especially in the tumors, because the purpose was to develop new type of cancer therapeutic treatments by using the double effect of iron oxide nanoparticles, because they can be used for destroy in a target way the tumor cells in a selective way respect to normal cells, because the iron oxide nanoparticle have this double action of they can be used like a carrier, but also can be used like an agent of hypothermia, and also can be conjugated with different drugs or other targeting moieties, and to balance the impact, especially the side effects that usually there are for the chemotherapy drugs in patients that produce a lot of consequences for patients. The purpose is also to use nanoparticle to conjugate with different targeting molecule. They can be also antibodies, can be the new type of biological molecular biology, like different targeting in cancer cells. They are they can be find on the surface membrane of the cells, and another concept is to use magnetic hypothermia, because magnetic nanoparticles, they can be used for this effect of magnetic hypothermia, and under the effect of an external magnetic field, they can release energy by heat. And it can be modulated because it's an effect that you control from external, and especially they can be released only in the target site of the tumor, and so to do a very specific effect that is a very advantage compared to other therapy. But also this technique can be coupled also with radiotherapy or photochemistry. There are different type of application, and the purpose so is to use the core of iron oxide nanoparticle and conjugate with the different moieties, can be also radio or other type of conjugation. And the purpose is to be inside to these functionalized nanoparticles, to be targeted inside the tumors, especially to overcome the cell membrane, especially the blood vessel. Another strategy is to use functionalization that recognize receptors, specific receptor of the cell membrane, and so to give this specific killing effect of cancer cells. Iron oxide nanoparticles have different advantages, because they can be used like tracers, using classical nuclear magnetic resonance, and so in this way it could be implement a guided to killing cancer tissue using this electromagnetic field, and so to destroy in a selective way these cancer cells by using any type of antibodies or other cancer biomarkers, like a selective delivery, especially to solve problem of pharmacokinetics. Is more related to biological point of view. And there were recently published this article on Nature Nanotechnology about a very interesting application of a such type of patent drug approved from Food and Drug FDA, and they try to use on tumor tissue, and they observe very good results for the killing of these cancer cells, especially because they test this technology in vivo in animals. About the strategy of the project was to use different approach. The first was the opportunity to have target chemotherapy by using classical drugs, but in low doses of this chemotherapy. The second was that I was previously mentioned about hypothermia opportunity. And the third was the opportunity to couple this new technology about the modification of gene therapy. More focused about the general application of this technology can be used for from industrial application. So it's very interesting because about the cancer, it could be also very good to implement about new technique of tissue engineering, but also by bioscience, also other similar extension and perspective of this technology. Now more about the chemical synthesis. They were based on co-precipitation of iron ions in alkyl media. We produced these almost spherical nanoparticles with a diameter around 15-20 nanometers, and an additional was to use Stauber method to give an encapsulation of iron oxide nanoparticles of silica by using TEOS, like a precursor, silica precursor, tetraethyl orthosilicate. In this way, we give a more biocompatible nanoparticle, because usually in literature we observe that naked iron oxide nanoparticle can sometimes give some problem of toxicity. In this way, instead we block the problem biocompatibility. It's very more stable. And also to better functionalize, we had a third synthesis procedure by using two different precursor calcium citrate. They were including in the core shell of silica, in the crystal structure, and also to stabilize the colloidal of this nanoparticle, we used also citric acid to dispersant agent in the solution. And the four type nanoparticle that we produce with the different a consequent synthesis production. We start from naked magnetite iron oxide nanoparticle, and so we add all additional core shell functionalization, and so we characterize the different property about morphology and size of nanoparticle with different techniques of scanning electron microscopy. We confirm also the chemical composition by using a spectrum and a IDS probe, and also very important, the super paramagnetic behavior of this nanoparticle to apply for the purpose of the project. And also the heating ability by varying the magnetic field of this iron oxide nanoparticle, and also the colloidal stability of this nanoparticle. About the technology, we observed just an agglomeration, and so we confirm from said patterns. They show broad halos comparing to magnetite according to literature, and also these are other images of field scanning electron microscopy. They confirm around the range of diameter, because these nanoparticles are more around 15-20 nanometer of diameter. With this another with STEM microscopy, and also we confirm the presence of the peaks around with ADS. We confirm iron here, so iron, but especially oxygen from the oxide. this is the confirmation of the peak of silica, again of iron, and especially in this case the good result for the production and the inclusion, the crystal grid of the calcium in this ADS spectrum. These are 10 images that confirm around the diameter with the bass scale, confirming also the presence of such type of crystal grid due to the presence of the silica. And again, we confirm with another ADS probe spectrum that we observe presence of iron, and also again with this crystal grid, and also again of silica and calcium for this image. Also, we used to magnetic flux microscopy to observe the behavior of this nanoparticle with the presence of the classical atomic flux microscopy, but also with addition of magnetic flux microscopy to observe the different behavior, especially for the behavior about the tip of the magnetic flux microscopy. Especially is more defined in the case of calcium, the definition of the image for magnetic flux microscopy. And so we use the magnetization behavior, and so to confirm the superparamagnetic behavior. In this case, we observe a classical confirmation of superparamagnetic behavior. And just for we observe just for the saturation magnetization was just more reduced for silica, and yeah, it's probably due to the core shell that block the magnetic field of these nanoparticles. So we investigate about the colloidal stability of this nanoparticle, about the relationship between the value of zeta potential measured with a classical zeta meter instrument and the value of the colloid. And so we observe a trend, a negative value with modification of isoelectric point. And related to the stability behavior, we confirm that in the starting pH they have a moderate stability for the naked and silica core-shell nanoparticle, and a very good stability more about calcium doped nanoparticles, and also about the behavior to this nanoparticle by modulating and increasing the magnetic field. We observe also an increasing in the SAR property, and there is a direct relationship between the increase in magnetic field. And also these nanoparticles were tested more for the property of biocompatibility, where they were tested to the University of Piemonte Orientale about in contact with endothelial cells. They used two different approaches, and they confirmed a good trend of cell viability compared to control for all type of the two approach of cell viability evaluation for all different experimental time tested. And also we used an approach of dynamic cell viability condition by a bioreactor that simulates the shear stress of nanoparticle diluted in normal media for cell culture, and in this way we observe if they produce problem of dynamic survivability condition, but the data confirmed for the two different tests used for the survivability that they show survivability comparable to control with two different tests. We use also scanning electron microscopy to observe if there would be such type of accumulation, because this is a big problem about when we have possible future clinical development or next clinical drug stage. And because here we observe just for iron oxide, instead more stability for silica iron oxide nanoparticles, so we didn't observe any type of this accumulation, and so it was confirmed from the ADS spectrum, and it's confirmed this data of the presence of iron only for naked iron oxide nanoparticles. These nanoparticles were tested so in vivo with different approach. I show this especially this data about ICP spectroscopy accumulation of the different type of nanoparticles in the organs of mice used for in vivo test. And so about the conclusion of this work, we were able to produce stabilized magnetite nanoparticles with diameter around 15-20 nanometer by using citric acid like dispersion stabilizer. And so we are also able to produce with core shell type functionalization. The magnetic hysteresis of the nanoparticle measured with vibrating sample magnetometer confirmed the superparamagnetic behavior of this nanoparticle. Also, the third pattern confirmed the crystallographics signal compared to literature, so especially of the magnetite and magemite crystal forms of the iron oxide nanoparticles. And also that these were cytocompatible, biocompatible nanoparticles, and they were good with good colloidal stability, with a range around minus 30 and minus 50 millivolts, and also the heating ability, especially for the application of thermoablative and hypothermia treatment, and the magnetic revelation with atomic flux and magnetic flux microscopy were good to determination of magnetic property of attraction or repulsion of this nanoparticle with the tip of the magnetic flux microscopy. And about the final conclusion of this work, we were able to implement tools of nano platform for aspects incorporation of innovation on a nanometric range scales, and these nanoparticles were optimized for like a carrier for chemotherapy or with different gene therapy application, and also for thermoablative, but especially in the fine it could be one of the big future perspective for development of new scientific perspective, therapeutic application of this drug delivery platform for cancer, but also for different in vivo disease. And okay, and this is conclusion.
Okay, thanks. We have time for a few questions.
So you said that actually in around the core there is a magnetite. So I imagine that the tumoral part is, so to speak, in advance, is prepared in advance with some kind of preparation method in order to select the nanoparticles around the tumoral areas, and then it's a magnetic field applied also, I imagine. How it's done? practically? So how can you be sure that most of the nanoparticle reach the tumoral area?
Generally, when they tested a final design of this nanoparticle with previous articles, they usually inject directly the nanoparticle near to the tumor site. But more efficient application to target cancer cells could be especially to use antibodies, because antibodies are able to recognize any type of receptor of membranes, especially if this works is integrated with the works of molecular biology, because it's possible by sequencing the DNA of a biopsy of a tumor to observe which is the receptors that are recognized and expressed in the surface of the cell membrane of tumors, and so you can integrate these works on nanoparticles with these receptors, and so it's possible to recognize in a specific way. But there are also other type of applications. There are new type of another technology. It's an evolution of antibodies is aptamers. They are DNA that are able to recognize any type of targeting receptors. So there are different opportunity for this aspect.
Okay.
Usually, there is the reticular endothelial system. That is, it is more related to immunological point of view, because in the body, the first organ that came in contact and that purify, that filter, clearance all agents that are in contact with the body, it's liver, but especially spleen. And in fact, we observe in the ICP, we observe some more. This is the confirmation. We observe some more accumulation of iron in the spleen. Just now, it's in the trend of liver, but in spleen, it's the first organ that came in contact that activate for the response of the nanoparticles.
Okay, we have an answer for live from YouTube, for a YouTube site taker that ask how with the superparamagnetic nanoparticle you can burn the tumor. So briefly, if you can explain hyperthermia.
Yeah, the concept is hyperthermia. It's when they are activated in a specific range of magnetic fields, you can modulate this property, and also you can modulate how much heat they are released, and for just the right experimental time, because there is like the tumor, every tumor cells responds in a different way about how many minutes they are in contact with the magnetic nanoparticle or any type of nanotechnology opportunity. And so you can modulate, and you do a specific work of killing this, because this technology can be applied for different type of tumors. Now I moved recently to University of Oslo with a Marie Curie project, and we try to apply this technology for breast cancer, because breast cancer is one of the big causes of cancer in women, and it causes a very high incidence of cancer death and mortality.
Okay, thanks again with the speaker. Okay, we can move to the other speaker, that is Valentina Elettra Bellinzona of the University of Pavia. Okay. The talk of Valentina was about the switch this one. Okay. The development and the implementation of a non-Gaussian model for the lateral dose prediction in a proton therapy treatment planning system. Wait for the slide. Okay, let's go.
Okay, I would like first to thank the organization to giving me the opportunity of presenting my work today. My work in particular is my PhD work that was developing co-tutor agreement between the University of Pavia, the INFN group of Pavia, and the Ludwig Maximilian University München. And it deals with a non-Gaussian, and about the developing and the implementation of a non-Gaussian model for the lateral dose prediction in a proton therapy treatment planning system. But let's go step by step. This presentation is mainly divided in two parts. The first part aims to answer to the three great questions of the life, in my opinion, that are what, why, and how. Unfortunately, today I will be able to answer only in the framework of hadron therapy. So, first, what is hadron therapy? Honestly, I really fell in love with this picture since, in my opinion, well explains the concept of hadron therapy. I guess that everybody of you knows already the normal radiotherapy. Hadron therapy is a cancer therapy treatment that uses light-charged particles, so like protons and carbon ions instead of the photons, to cure cancer. So what does it mean, this picture? If we if this is the dose, we are able to avoid to touch all these balloons and destroy only the red one that contains the cancer. Why? The first answer is a radiobiological one, since the heavy ions has a really good RBE. What is RBE? In common words, if you deliver the same dose of protons or carbon and the same dose of photons, you destroy more and more cells, I would say, with carbons instead of Y-ray. And also, they have a really good LAT with RBE range, that is this one. So, you are able to destroy a lot of cells and a lot of tissues without overdosing or underdosing. But the second answer of the question why is the physical point of view. Under physical point of view, these particles has a really nice behavior. Why? Since the normal X-ray deposits the dose in this way. So we have a high dose, if this is the tissue tabs, on the skin. So at the beginning of the tissue. Instead, the particles are delivering really low dose at the beginning and a peak of dose in the tumor area. That is called the Bragg peak. So this is an example of a treatment. If this is the region of the tumor, on the left side you can see the X-ray treatment, on the right side the carbon ions. So we are able to, they are able to concentrate the dose on the tumor area. And the last question is how. How is with a treatment planning system? The treatment planning system is a system that try to deliver the maximize the dose in the cancer region and minimize the dose to the healthy tissue around. Let's have a look on the workflow of TPS. As input, you require the patient data. So for each patient, you have to acquire the CT scan and the outline of the patient, and then the localization of the tumor and the critical structures that you don't want to destroy, obviously, and this is made by doctors. And on the other hand, you have the beam data, so the radiation quality, which particle would you like to use, and which kind of energies you can. And then the system starts this process. So it optimizes the source and the beam placement, and then it makes a simulation in order to find the dose distribution calculation. Pay attention, since this is a loop. So this procedure is repeated until the system finds the best solution that can be reached. This is a crucial point, since this is a lot of time consuming, obviously, since it's a loop, and it's based on approximated models. In particular, all the TPS available right now are using a double Gaussian model. That is not fully correct, obviously, since it's a parameterization. And I'm speaking only about the lateral loss profile, not the entire one, the lateral. So the beam axis is the X1, the Z1, so across the fall, and this is the lateral one, okay? And then we end up with the treatment plan. So we can go ahead and go to the second part of the presentation. That is the goal of my PhD. That was to develop a computational model able to overcome the actual limitation of the approximated model, and then implement it in a real treatment planning system. In order to do that, I have to spend some words of the developing of the model. This model is based, okay, first, this is the Z-axis. So our beam is starting from here and deliver the dose in this way, okay? So you have to figure out that here is the cancer region, and we will focus on the lateral dose profile. The lateral is based on the core due to the multiple column scattering processes, and then the tails that are mainly based by the nuclear effects. The electromagnetic core can be modeling by using the Mollier theory. So our particle is starting from here. So the first layer, this is, for example, the skin. And obviously it will be scattering. So this is the first scattering angle, that is a net angle. And then it go in the depth until reaching the detector. We can't predict, obviously, we can't follow particle by particle. It's a statistical process. So we need to predict the probability to find a particle in this area, and in order to do that, we have applied the Mollier theory that is able to predict the probability to find a particle in the interval angle d theta after traversing a thickness c. This is valid for any kind of particle and any kind of media. The two crucial factors of this theory are the Chi c square and Chi alpha square. The first one is related to the scattering angle RMS, and the second one is the parameter that explains the Coulomb potential screening. I just would like to focus on the variables, because since the capital letters belong to the medium and the normal letters belong to the particles, okay? So again, it's valid for any kind of medium particles. And here's some validation of this first part, so only the electromagnetic part, against the FLUCA simulation with the setup of a real clinical case, that is the Heidelberg Ion Therapy Center. In this picture, you can see the simulation in blue, and the green line, that is the model prediction. These are energies and depth of clinical interest. And this is an Eiger energy. But now, in order to have a complete description of this problem, we have to add also the nuclear tail. How? Okay, the nuclear tail are mainly based by nuclear collisions. We have done this with adding a Cauchy-Lorentz distribution, but adding in a proper way. What does it mean? It means that we have put this part with the previous one by weighting with the WP factor. The WP factor can be calculated studying all the nuclear collision useful for iodine therapy contest. And it has this kind of shape. So now we end up with the complete model. And the second part was to to validate that against also the data. Data are coming again from Heidelberg Iodine Therapy Center. And again, this is the FLUCA simulation in blue. The dots are the clinical experimental data, and the analytic model in red. And this is another energy. We're pretty satisfied. After obtaining these results, I've developed a code in order to put this model instead of the approximation in a shared treatment planning system available in Munich. So this is the normal interface of the program. In red is the tumor area. Obviously, this is a geometric case. And in blue, in light blue, you have the surrounding tissue that you don't want to touch with the dose. The setup of the work was to analyze a single beam, so one energy, several energy, but only once per time, with several depths. And then, as a second case of study, a full plan, like a real patient in water. And at the last one is the plan with inhomogeneities. So, for example, bone and fat that you can find in the body. In order to do that, each plan was analyzed first with a with a model calculation, and then exactly the same plan was evaluating with the double Gaussian, so the old parametrization. And in order to have a reference, we have used the Géant4 simulation. This is a good accord with the other Monte Carlo studies. And these are the results. First, one single energy in water. In blue curve, you can see the double Gaussian parametrization. In the red one, the model, and the green, the Monte Carlo. For one energy, for a higher energy, and then after the fat, so after the inhomogeneities, exactly the same, and after a bone. Obviously, there's an objection that is, okay, it's a nice work, but these differences are not so huge. Completely right, but these are single beams. In order to have a real plan, you have to sum more and more and more beams like this. So, if you are not accurate in this region, you are summing an error, ending up, as in this case, with, I would say, a different plan. Since on the left side, you can see just the net difference between the double Gaussian and the Monte Carlo, assuming as truth of Monte Carlo, and on the right side, you can see exactly the difference between the model and the Monte Carlo. This is a 2D view, so you are looking from the top to the bottom of the slides of the patient. And with this, I would like to thank for your attention, and if you have any question, please.
Okay, thanks for a nice talk. We have the time for some questions.
So when you mentioned the Molière model, you show a function which depends from the depth x, I guess, and from other variables like z and a, which you said are the variable related to the medium. Can you explain the definition? I guess maybe z is the total depth of the...
No, sorry. Z is just the mass number. It's just the mass number of the medium and the mass number of the particle. It's just a matter of definition. X or T is the thickness that the particle is traversing, and Z is the mass number of the medium. that is related to the scattering. And the modular theory, the formula that I've shown is just like a little framework of all the theory, obviously, and in my opinion was the most significant one, since it was underlining that are not depending or on some kind of particle or some kind of medium, but are completely common and general.
Other question?
So if I guess well, you didn't, in the simulation, you didn't choose the kind of particles, or you choose like protons or carbons when you make the simulations?
Obviously, you have to choose the particle in order to do the simulation. And
which did you choose?
In this work, protons.
Okay, because I was wondering the difference you see when you look at the dose curve, maybe with respect to the depth. If probably you use carbons, you will have maybe more discrepancy due to fragmentation. So if you can comment that, there.
Like this. You're completely right.
Yeah, for proton. Yeah, I was wondering if it was like carbon, so maybe you can explain a bit the discrepancy due to the fragmentation and low X.
Absolutely, yeah. I mean, with carbon ions, you can see a huge difference with the tails, particularly. Unfortunately, this TPS was holding only protons, and the model was validating on protons. Just to add a little comment, the discrepancy with protons is already quite high in this case. And the main problem with carbons is, okay, the lateral path for sure, but also the fragmentation tail after the peak. That is the most problem right now. Instead, these pictures are not okay. The discrepancy that you can see, the angle that you can see, is just is not a function, but is like a collection of the points, since you're taking a slice of the matrix of the dose of a program, like a slice of patient. And the program is set to store the low point dose in a different vector respect to the high dose point in order to save memory and time. Since you just have to keep in mind that my one was just a parallelepiped of water, but in normal case you have a person under the treatment and you have to be fast.
Okay, thanks again to the speaker. Okay, we have a missing speaker because Maria Perez Zabayos is missing. No? Okay. Okay. So we move to... No? Thanks. We move to Alberto Traverso with from Politecnico of Turin, and the title of the talks is Development and Application in Clinical Practice of Computer-Aided Diagnosis System for the Early Detection of Lung Cancer, State of Art and Challenges.
Okay, good afternoon, everybody. Thank you for inviting me here. So I'm a PhD student, almost finished. Spent my PhD Polytechnic of Turin, and the project is also a collaboration with the INFN of Turin, and I also spent half of my PhD in the radiology department at Rarbal UMC, which is an hospital in the Netherlands. I'm going to talk about this project, which is actually in the field of medical physics, but you actually heard about one big part of medical physics from previous presentation, which is actually radiotherapy, so the part of cancer therapy. So I'm going to talk about, I would say, the other side of the medical physics, which is the diagnosis, so basically medical imaging analysis, and especially about lung cancer. I have to say that's quite wide, I would say, field, because you actually collaborate with clinicians, so radiologists, but you also collaborate with computer science, so actually it brings sometimes a very big problem of, I would say, scientific communication, because you put together different fields which sometimes they talk different languages. Okay, in my talk I'm gonna try to answer some of the questions. So the first one is, how can we improve lung cancer diagnosis? The second one is, how can we actually help the clinicians to interpret these images? The third one is, when we found a way to help the clinicians, how can we introduce this solution to the clinical practice? Then how can we, of course, introduce some benefit in improving the diagnosis? And since I said it's quite deep field, we should also ask ourselves which are the clinical impacts. So let's start with the first question. Okay, I'll start with this sentence, which is quite strong. It says that lung cancer remains still one of the biggest health issues in developed countries, and I'm gonna, with these two pictures, try to explain you why. So the first picture show actually the number of deaths in the United States divided for a type of cancer, and the peak here is determined by lung cancer. So actually lung cancer is the biggest cause of cancer-related deaths in both United States and Europe. But I like more second picture, which is I think that is inside a big space for development and research. This shows the 5-year survival rate, so the probability that a patient that has been diagnosed with lung cancer can survive after 5 years the cancer is diagnosed. And here is divided for the cancer stage. And don't go into details, but you have to think that if you move across the axis, there is the last stage. In the last stage, the patient already has a very developed lung cancer, so actually the illness can be seen actually also from like some very deep problem and very obvious. But if you are in the first stage, actually you can't see the disease because it's in a symptomatic phase, but the cancer is still there. And if you compare, if you make the diagnosis in the first part, the 5-year survival rate is almost like 5-6 times bigger than when you diagnose this in the late stage. The problem is that we are still not good because most of the cancer diagnosis there, because actually the patients go to the hospital because has a real problem that the doctor can see, and we should be able to diagnose the cancer there when the survival rate is very big. So of course this is a very big research issue and motivated a lot of researchers. And on two sides, I would say. The first side was the medical imaging side, so was how can we find the best, I would say, hardware technology to detect lung cancer. And this is the computed tomography. Here there are some images, so actually you take photos of your body. And then the other part was the clinical, so I would say, how can we improve the diagnosis? And this is one of the most important results achieved. It was a national lung cancer screening trial in the United States when actually they compared the patients. They made first a normal X-ray of the body, and then they take this CT scan, computed tomography, and they show that if you screen a patient, usually heavy smokers, with computed tomography, you improve the diagnosis of lung cancer. Of course, this is the nice part of the job. The bad part was that actually you brought into clinical practice a big problem, which is being called data explosion. There's a nice paper, there's also reference. They say that actually, of course, you can screen a lot of patients, but you give to radiologists a lot of images to be analyzed. And radiologists actually were not ready, also under the software point of view, to analyze all the images. You have to imagine the image like a lot of slices of bread, so picture of your body, and the radiologist actually spends all the day looking at these images. And there are literature articles that prove that actually the concentration of the radiologists in detecting the lung cancer decreases as soon as the number of images to be analyzed increases. And this was really big issues. And the other big issue is that what are you looking when you trying to find lung cancer? In the early stage, actually you look at pulmonary nodules, which are some structure that appears brighter in the image. So, but of course you can see that this is a pulmonary nodules, so it's a sort of mass, it's quite big, so it should be quite easy to see. And this is called a solid nodule. But there are also some examples of these nodules, which since you are at the beginning part of the disease, actually they are not formed and not so big, but probably if you look at the same scan like some years later, you will figure out that this nodule has turned into this one. These are called ground glass opacities. So actually it's a very difficult task because you have things that are embedded into anatomical structure. Sometimes, for example, they are linked to vessels, so it's very difficult to separate them, at least from a visual inspection. So the second question is, how can, as a researcher, support this diagnostic process? And there was a big field that actually was born like around 10 or 20 years ago, and was to develop automatic algorithms for the detection of pulmonary nodules in computed tomography scan. There were actually two goals. The first one was to make this interpretation faster, and the second one was, of course, to improve the cost effectiveness of the screening program. So without going into details, which is the basic idea of these algorithms, actually as input you have a CT scan, so the image of the patients. Then you select some possible candidates, so your algorithms say these can be some possible nodules. And of course, these are not only true nodules, so you go into this phase, which is called phase positive reduction. So actually from a very, like 1,000 of possible candidates, you perform some classification and you get a final list of marks, which your system say they are more likely to be nodule, and you send this list to the radiologist. Here is an example. So actually, radiologists will look at the images and will have the CAD marks highlighted like this of different nodules. And you will have to say, okay, that's a true positive, so I'm going to include in my annotation, or that's a false positive. And of course, there were studies that tried to put this system into clinical practice, and actually they show that if you support radiology with this system has a benefit, because actually they had some nodules that were originally overlooked by the radiology and they were missed. And some studies also show actually that the most of these nodules were the nodules I showed you at the beginning, so the very dark one. And there is also some pathological studies that show that these nodules missed by the radiologists but found by the algorithms are found to be the more malignant in the future. But sounds very good, but if you look at hospitals and you say, so how many hospitals are using actually these kind of systems, you see that apart from some hospitals in the United States, actually these systems are not using clinical practice. So actually, if I have to summarize my PhD project, I can use this question. So even if we have these very prominent results, why these systems are not using clinical practice yet? And actually, we can underline some of the reasons that I divided between the status of art, so how actually the systems are using clinical practice, and on the other side, how can we improve these systems. The first one is that usually in the hospital you have the standalone workstation. You buy a CT scanner, and like the manufacturer of the CT scanner gives also you the algorithms together, so it's a workstation, so actually a computer, a desktop. Then of course the algorithm is very complex, so you have to buy hardware, so actually the hospital has to buy also hardware. And it's a static hardware, in the sense that you can buy a very powerful computer, but the problem is that in clinical practice you don't analyze so as many CT scans as you do in lung cancer screening. So actually you pay a very powerful computer, maybe you use 100% of the power when you have a screening campaign, but what happens during the clinical practice, well, actually you have low CT scans. So you pay a lot, but you don't use the power because it's actually static. And then the other point is more, I would say, clinical point, which is that if you buy standalone workstation, it's quite impossible to share results between radiologists. And this has a very big clinical impact. For example, think about a small facility. Sometimes, usually, they don't have residents or expert radiologists, and maybe they can benefit from having a revision of the images from experienced radiologists all along the Italy, but also the world. So the challenge we tried to face was, first, how can we make these results of this system available without requiring any software installation, any hardware installation? So actually, how can we have some elastic computing resource that adapt to the workload that is required? And the third point was, how can we make the possibility to share this annotation between different facilities? And another point is that can we combine the algorithms to improve the performance? This is an overview of the project. So the M5L project was actually started from developing a full system and validated an algorithm. And this is the core of our scientific validation. So actually we train our classifier and our algorithms, and then we validated on around 1,000 CT scans. And this showed the sensitivity. So how good are you at detecting the node with respect to the average phase positive per scan? What does it mean? It means that if you look at 4 phase positive, I mean the radiologists have to click away around 4 CAD marks for each exam. So usually the working point accepted by radiologists, because of course you can't ask to a radiologist to have a high sensitivity but to click away like 20 or 40 phase positive, because it will be totally not effective. It's around 80% at around 6 phase positive, which is an offsetted, I would say, range. And then we start ourselves to face the challenge. So actually we developed this system which makes use of one thing which I would say it's very known and used every day, which is the web. And the other one was, I would say, a new technique in computing, which is called cloud computing. I'm going to go now a bit into details about the web front end. So actually we develop, after having written the algorithms, we say, okay, how can we make available without requiring any software installation? So we make a big front-end web, where actually is formed by 3 big parts. In the first part, the radiologist can just log in with the credential. He can submit the cases as soon as acquired in the hospital from the patients, and he can select some radiologists, not necessary for the same institution, that can review the exam. Then after you submit the exam is copied in this cloud backend. And actually we set up in the computing center in FN. So the idea of the cloud is quite easy. Actually it's like you are renting a computer just for the time you need to do the computation, and then the computer is totally free. Just to give you an idea, Amazon, the one everyone uses for the e-commerce, is based on the cloud computing. So actually they have some available resources, but for example, I don't know, when you have the Black Friday, when everybody is going to shopping online, more resources are added because you need more power. And this is the idea of cloud computing. So actually you just host the computer for the time you need. If you need more power resources, they're given to you, but then they are free because other users can use the resources. For example, in physics at INFN, we share with particle physics. And the second part of the web front end was to give the possibility to the clinician to directly annotate the exams, also working from home, by the way, because this website is accessible also from mobile tablets. So actually, as a viewer, he can look at the exams as he does in the clinical practice and can insert the medical annotation. And then the third part was when he stored the annotation, he received an email and they say, okay, you stored the annotation, now I give you the CAD results and you can have a look and review them. And we perform already a prior matching, so actually it doesn't make sense to ask the radiologist to say, is it a true positive if a nodule has already been annotated? It makes sense more to only propose to radiologists the CAD marks that were not matched with the previous one. So actually, we asked to the radiologist, did you miss that nodule? And if yes, it's marked as a true positive, and also he has to explain a sort of malignancy to classify that. So the final annotation is radiologist plus review of the algorithm findings. So now we go, okay, we try to introduce this in clinical practice, but how can we increase the detection performances? This is the part I almost developed in the radiology department in the Netherlands, when I spent part of my PhD. And when I was working on that, there was actually an article by a famous radiologist, and it was called, you can't see, but the key points are computer-ready detection of missed lung cancer. When I saw this title, I was a bit saying, okay, are we doing something wrong? Because I'm saying to you that the systems are very good, and now there is a paper on radiology that say that computer-ready detection of missed lung cancer. If we go a bit in details, they say computer-ready detection systems detect up to 70% of lung cancer not detected by the radiologist, but they fail to detect about 20% of lung cancer. So he says something like, okay, you can use computer-ready detection system, maybe, but actually they miss a lot of lung cancer. So I went a bit into details, I read the paper. I took a bit personally, by the way, this thing. And I was going there and I say something like, okay, but the CAD system that were evaluated was quite old. They were like 4 or 5 years old. But what about if we include like some news technique? And for example, one of these techniques is called deep learning. There was a Nature paper some years ago. I'm not going into details, but the idea of a classifier, usually you take neural network, you simulate how our brain works. So you see something, you train to recognize according to some feature, and then the classifier is saying to you, it's a nodule, it's not a nodule. Deep learning is a new technique that was used also by Google. When you type the image on Google like cat, it's based on a deep learning algorithm. So it takes all the images and classify the image if they contain a cat, and they show you the list of images with a cat. And they're very powerful, but they were only used, I would say, to identify normal images. So I start asking myself, what happens if we use these technologies to identify medical images? And also, how can we evaluate different systems? And what about if we combine them? So we organize together with some radiologists there in the Netherlands this medical challenge. The idea of medical challenge is that actually you propose a problem, which sounds quite difficult, to the community, and people have to develop their best algorithm to solve the problem. And we decided to ask, the problem was to identify, of course, pulmonary nodules in CT scans, but we divided into two parts. The first part was to ask if the people want to develop a complete CAD system, so actually for all the parts I described, and then how to involve the people working about deep learning. Actually, they don't have so much experience about medical imaging. And so we decided, okay, let's give to these people the list of candidates from other CAD systems, and let's ask them to perform only the classification, so the phase positive reduction. And then was to appeal the people from that community to face medical imaging process. And actually, we figure out that when we open the subscription for this challenge, when we start introducing the second part of this track of the challenge, there were a lot of people for machine learning communing, doing basically other things like classifying images, pictures, or something like this, but not from the medical side. They subscribed, and they decided to take part into this challenge. Actually, using the same classifier they use for other kind of problem, like classifying cats in images. They train on our dataset, which was selected to be very, very, I would say, big. So this is all the scan manufacturer. You can see that there are several brands, just because you want your algorithm to be able to classify all the scans, not only scans for a particular manufacturer, because you want to use deep wide. And okay, so we start asking which is the best possible algorithm. I'll show two curves. These are similar to the curve I show you in the validation of my system. So this is again the sensitivity, and this is the average phase number of phase positive. This is for the first track. So these are all the people that submitted the, I would say, classical CAD system. They didn't use any kind of deep learning, and you see that actually the system are almost good, and they reach around 80, 90%, but around 4 phase positive per scan. On the right side, you have the people taking part only in the phase positive reduction track. They all use deep learning techniques. We also developed one technique inside the hospital. And as you see in the performance, they are very, very higher. If you look at the black curve was a study about combining all these systems, so taking all the combination of the finding of the system. And if you look at this curve, you say that there is no comparison between the classical systems and the new system. But the point is that you still need the classical system, because this system takes as an input the candidate found by this system. So actually what these curves say to you is that you can use traditional imaging technique to find the candidates, and if you combine them with state-of-art deep learning algorithms, you find the performance of your system, which is around 10-15% higher than the traditional performances. We also said, okay, does this, let's say, best algorithms work in clinical practice? So we propose to the radiologists, 4 radiologists there, we extracted all the phase positive, one phase positive per scan, so around 888 nodules, and we asked to radiologists, are these true nodules? So did you miss them in the original notation? And as you see for the number, there are at least around 40 nodules that were missed originally by the radiologist and the system seen. The last part are which are the clinical impacts. So now we figure out that this system works very well if you use state-of-art techniques, but how can we use that in clinical practice? And this is the last part of my PhD thesis. It was in collaboration with the medical physics department. This is Candiolo Hospital. It's a very excellent research center in cancer and also a hospital in Candiolo, which is near to Turin. It was in collaboration with the radiology department, so Professor Reggia and the medical physics department. And what we took 200 cases from oncological patients. So there were patients that had the cancer, but it was not a lung cancer. It was a cancer on another part of the body, like, for example, breast cancer. And we say, are we able to detect pulmonary metastasis? So actually, you look at pulmonary nodule, but as expression of another cancer. This was motivated by the fact that in clinical practice, when you don't do lung screening, you actually want to look if oncological patients has developed a very aggressive cancer when the pulmonary nodules, when I would say the cancer moves to another part, especially in the lung. And so you're looking at pulmonary nodules as expression of a very aggressive cancer in another part. So actually, we submitted this case. The technical radiologist was acquiring them and he was submitting to us. And 3 radiologists were annotated these studies, first without looking at the CAD and then looking at the results. And then they couldn't make a comparison, so naturally they could see the first annotation they made, the marks of the CAD, and then add them to the annotation and make a final annotation, which was the radiologist plus the algorithms. This is a very complicated table, but there are 2 numbers highlighted in red. So these were the first results of the 3 radiologists on 700 scans, so actually less than half of the statistical population. These show you the nodules this is 17 nodules, so these are the nodules that are on which the 3 radiologists agree. And when you look at the gold standard reference formed by all the 17 nodules plus the nodules added that were originally missed by the system, you reach 36. What does it mean? It means that your system gives 19 more nodules than what originally missed, and the sensitivity of the radiologist plus the system reaches a 95%. I was very happy with these results. I have to say I was more curious because, of course, as a physicist, you always want more statistics. So we move on 200 scans. I only have the results on 2 radiologists. The other one is still reading, but I hope we will finish soon. But actually, you see that there is still a positive impact, around 19%. So plus 17% of the nodules are added by our system, which managed to reach a sensitivity up to 88%, which is a very high sensitivity. Usually radiology sensitivity was between 70 or 75%. So to conclude, well, we decided to propose a new CAD system which was called on demand, because actually the hospital could use the system when it needed, but it didn't have to buy any software or hardware. So it was cost effective and also, as I show you, improved the diagnosis. This also has some benefit on the lung cancer early diagnosis, because you see a lot of nodules like the very small one that can be and were proved to be malignant. So actually, one of the basic ideas of lung cancer is to determine the best treatment for the patients. It's not good to say, because I could say something like, okay, I found a nodule, let's make a biopsy. My biopsy is something that is invasive for the patients. And what about if the nodule is not malignant, as I was thinking? So actually the idea of proved clinical benefits, that you find a nodule, you classify correctly, and you say to the patients, no, don't worry, just come in 1 year, because it's not found to be malignant. And then we show that it's not true that CAD of missed lung cancer. I would say we can really talk about the CAR system of lung cancer, because we show that if we use state-of-art imaging techniques, so I don't know, I'm gonna finish that. Okay, here there are the references if you are curious to read something about that. And sometimes I think if we just can be more, I don't know, use some more fantasy to improve the problem of medical imaging. And this is a picture I found that was quite funny, to use the twister to help the patients put him better in the... It's just a joke, of course, don't worry, it's not gonna happen for... Thank you.
Okay, thanks for your interesting tours. We had time for 2 or 3 questions.
The first one,
yes,
is what is the possibility to move this, say, AD system to Linux, or looking for less expensive programs, because maybe this is the cost that is.
It's all open source.
Ah, okay. So open
all
source.
the libraries are classical libraries for medical imaging, so open source. And the website and the cloud backend, the website is done in Drupal, which is used, for example, for New York Times, weather.com, and it's all open source, all developed by us. And the cloud backend, of course, we bought the hardware, but then it's all open source, so it's totally open source. Yeah, no, we decided at the beginning not to make any, I would say, expensive software or to buy, because otherwise you could say to me, okay, you say about sharing CAD without software, but then you're using some software with license, and it will sound a bit inconsistency. Yeah.
And what is the time that you expected when you do your analysis, when you're running 200, for example?
Okay, so the time for computation of a case is around 20 minutes. There are 2 algorithms, they run in parallel. One is a bit more slow because it's a bit more complicated. It's 20 minutes, so actually from when you submit the cases, you have to wait 20 minutes. Of course, we didn't improve the parameter of the cloud, but you can assign like a priority, so you can say if the case wait more than that time, just process. But the average time is 20 minutes. But it's still suitable in clinical practice, because the radiologist will never read the case immediately as acquired. Usually they dedicate like some days to read and annotate the cases. So I'm not worried about a time of 20 minutes, because it's totally suitable with, I would say, the meaning reading time of a radiologist. And then he doesn't have to wait. He can just read other cases, and when the results are ready, he can just come back and read it.
And the last question,
yeah?
Sorry, it's what is the less resolution that you can see the nodules in the lung, for example, compared with the image? You know, what is the, because I don't know what is the size that begins the cancer, no? I mean, how do you differentiate?
You mean, okay, so there are 2 parameters which are important. First, I would say how you're sensible with the dimension of the nodules. There are some guidelines that show that you should annotate nodules starting from 3 millimeters, and that's okay, that's fine with our algorithms and also the algorithms, because they use. And then another parameter is the quality of the image. Of course, if you give bad quality of the images, your algorithm could be failed. But in our challenge, we took one of the biggest available dataset, which has a very range of quality. You can go from high quality, and you can go also from bad quality, and actually we are able to detect, yes, I would say the nodules are independent way from the quality. But the size of the nodules you want to detect is above 3 millimeters. We also find sometimes nodules that are 2 millimeters, not low, because otherwise they are too embedded into anatomical structure, but from 3 millimeters on, the system, yes, is well tuned to define that.
I was just a curiosity about the last upcoming future challenge.
Yeah.
About to distinguish about if they are benign or malignant nodules. I would like to know about how can you implement using deep learning, and especially, like just a suggestion, it could be interesting to integrate this very interesting, very exciting your application of diagnosis with such type of bioinformatic platform, like for example like DNA sequencing of tumor markers from blood or other similar examples?
Yeah, very good questions. So the first, deep learning makes a big difference with respect to traditional classifier, because you don't give the features. If you make your architecture as complex as you can and you give a lot of data, the classifier is able to learn the important features by itself. So it's difficult to say when you use a deep learning system which are the most important features, because the classifier learns by itself. You can make this analysis. In first approximation, I would say that there are also some studies that show that, for example, at the margin of the nodules, if the margin is a bit speculated, so it's not totally round, that can be an potential indicator of malignancy with respect to a benign nodules. Of course, this is a problem of this system, well, I would say these are a sort of black box. You put your data. Of course, you have to tune the classification. You have to tune the training data set. For example, if you give only big nodules, your system will learn only big nodules and not small nodules. But it's difficult to see which are the features that are most important. You should then go back. So you take your output, you should go back, take the various filters they are using the layers of the architecture and try to, I would say, make some merge on clustering to see how the filters see the malignant nodule with respect to the benign nodules. And that's for the first question. The second question, of course, that's the future. I mean, it's going to become a big research project about radiomics. Radiomics is actually was this very interesting paper about in Nature. They say that if you combine the visual assessment, so the radiologist, with the property of the DNA, you can actually classify the type of tumors and relate to the best treatment. In this, I would say that the work would be to ask ourselves which are the features that you see in biology or computational biology, and how can them be translated to the image. So if you see some property of a particular type of cancer, which are the quantitative features that are important in the image and can give you this property. But that's actually the future. Radiomics, I think, is going to be the future for making I would say, a patient-based treatment and not, I would say, a classical cancer treatment. So basically, because DNA is the peculiarity of every person. So yeah, that's the future, actually.
Okay, thanks again with the speaker. Okay, we now move to the last speaker of this afternoon. It's Veronica Ferrero from University of Turin with the INSIDE project, online monitoring and simulation validation with the INRiM PET scanner. I change your simulation.
Okay, so I've got the burden of the last talk, so I'm going to try to be brief. So I'm going to talk about the INRiM PET scanner, which was built for the INSIDE project for online monitoring in hadron therapy. As we said before, the difference between radiation therapy and hadron therapy lays in their dose deposition profile. We can see that photons release energy mainly at the entrance of the tissues, while charged particles have an energy peak release at the end of their range in a position called the Bragg peak. This translates into a higher sparing of the healthy tissues for charged particles, which is particularly important for pancreatic cancer. This is an example of a bone marrow cancer for a child, and the sparing of the tissue is important because children are growing very fast, so any unwanted dose can lead to a higher probability to develop more complication as a secondary cancer. So in the last few years, there has been a higher treatment with charged particles and also a higher build or facility that use charged particles. In Italy we have 3, and 3 isn't really a very high number compared to radiotherapy. So we could ask, why isn't hadron therapy mainstream yet? And one of the main problems that has yet to be addressed, aside from the costs that are higher for hadron therapy with respect to radiotherapy, is the range uncertainties. This can be related to many factors like miscalculation methods or more clinical factor like patient misalignment and internal organ motion and so on. So if we had a dose distribution that wasn't optimal, then we would have a overdosage of the healthy tissue that, as said before, we really don't want. So it is really important to have a kind of imaging system to detect the range in the tissues. And what we can do, we can exploit the interactions between the charged particle beam and the tissues. We can have different kind of interactions, like we can have the fragmentation of the tissues or also the target if the particle are carbons. We can have prompt gamma, and also we can have beta plus emission. We are going to focus in this talk in this last topic. So the requirement for a system, a detection system, it has to be very fast because we want to have an online response, and we are going to see why in a moment. And we also want to have a very good resolution. So tissues are mainly composed of carbon, oxygen, and nitrogen. So there is an isotope production, and this isotope decay in time beta plus. So basically what we have is a back-to-back gamma production that can be detected by a PET system. This is typically done after the treatment, which leads to 2 kind of problems. The first one is that if the dose distribution wasn't optimal, it's too late to correct it. And the second problem is that the isotopes that are produced do not have a very long half-time. So the signal that will be detected, which is strictly correlated to the Bragg peak, will be a signal that is decayed in time. So the optimal solution would be to have a PET system that can function while the treatment is being delivered. And from these premises, the INSIDE project was born for a dual system made of a dose profiler and a PET detector integrated in the treatment room to provide an immediate feedback on the particle range. Now, the dose profiler is currently under construction, while the PET detector is being tested at the CNAO. And here we see the PET installed in the treatment room at the CNAO in Pavia. These are the 2 heads, and from this direction comes the beam, which is perpendicular to the detector. So just to summarize, the signal that we take comes from the beta plus decay, and what we do is we reconstruct an activity 3-dimensional distribution. So how is the workflow? We begin from the treatment plan. We do the measurement, so we acquire the experimental data and we reconstruct the activity distribution, and this is done in real time. On the other hand, we have the simulation, which is run in Fluka, and also coming from the treatment plan, we have a reconstruction of the simulated activity distribution that is expected, so we can compare the two. So just a quick word about the simulation. We both account for the geometry and the characteristic of both the detector and the beam, which has a certain temporal structure. And we can see there is an in-spill phase where the bunch, the particle, are actually delivered, and an interspill phase. And the simulation is divided into two steps, in which, in the first step, we simulated just a fraction of the primary particle, that is for calculation time problems, and then we do a scoring of the isotope that are produced by the interactions, and then we simulate the decay of the isotope in time. And so we can reconstruct the activity distribution, and we can then compare to the experimental data. So this is just a very quick example of what we are expecting when we do a beam test. This was done, this is data taken from the very first beam test that we did with the completed PET detector. What we had here was a plastic phantom, and we delivered two mono-energetic slices of protons. So here we are seeing the activity distribution, which is reconstructed, and this is the section which is parallel to the two heads. So the beam comes from this way, and here we see the first slice and the second slice. And if we project this in the beam direction, so we see the activity profile, we can see that there is a neat activity distal fall off, and that can be correlated to the Bragg peak. And what we saw was that the measured difference was within 1 millimeter with the expected difference, which was a really good result. Now, this is a very easy case because we had a plastic phantom. We didn't have, of course, a living, breathing human being. And also, we had just two mono-energetic slices, which is not what happens when a treatment plan is delivered, because a treatment plan is made of many different energetic slices. So it's actually a little bit more difficult. What we see here is an example of two different treatment plans. Here we also have plastic phantoms and two different treatment with different range energies. In each of these images, we can recognize three different sections corresponding. Again, this is the plane that we are interested in which the beam comes from this way, and these are the coronal and transverse section with respect to the beam direction. So a nice story about this beam test that I always like to tell is that we did this beam test during a night shift, and we were all very tired and all of this, and so we were reconstructing the images, and we were trying to do a repeatability test. And so we were like, the first two images seemed very alike, and we were very happy, and then we were reconstructing the third one, and we were like, okay, so we must have done something wrong. But we actually went and asked and the technician, and they said that they mistakenly gave us two different treatment plan delivered 2 times each instead of one treatment plan delivered 4 times. And we were able to see the difference online, so while the beam was still going on, and we were very happy about that. So this is the data and the simulation, one next to another, that we have to compare. What we can do is we can see, as we saw before, the activity profile along the beam axis. And please notice that these 2 images are not normalized. So we have a very good qualitative accordance for all the 4 treatment plan with the simulation. What we don't have is a very neat distal fall-off that can be correlated to the Bragg peak, because we have many different energy slices. So if we want to have a quantitative study, we have to do a different approach. And so we did a 3-dimensional comparison by constructing an activity mask, in which we also use a threshold filter that is to get out all the noise outside the wanted volume. And so we build these 2 masks, each correlated to the images that we want to compare. And what we do is we subtract each of the voxel belonging to the masks in the beam direction. Now, the problem is that we don't have to consider all the volume, because most of this activity that is seen in the transverse plane is actually an artifact from the reconstruction algorithm. So we use the information from the dose delivery plan, and we select only the volume there is in which the beam actually delivered something. And if we do this kind of comparison, then we see that the distribution of the difference between the 2 images has an accordance within 1 millimeter, which is nice. Okay. And we also did this for the 2 treatment plan that were repeated, and the accordance this time is a half millimeter. So to conclude, well, we showed these last results to the CNAO staff, and they were really happy, and they said they were going to try to find us patients to test our detector. So we are just waiting for the authorization. And so just to conclude, we saw how the range monitoring was important, and we built the detector, which is an in-beam PET, with which we did a qualitative and quantitative accordance. Okay, and thanks.
Okay, thanks for your nice talk. Questions? No. Okay, I made to you a question related to your work and other work that people told us today. What do you think about the comparison between hadron therapy and, for example, nanoparticle therapy in using in treatment of cancer and other disease?
It's 2 different things. Like, well, nanoparticle therapy is target therapy. So nanoparticles are usually, like, you mean for the outcome?
Yes, for the treatment of, for example, cancer. I know that, for example, with
well, actually, the best thing would be to do a combination of therapy, like nanoparticle therapy is not given alone. It's always given with radiotherapy or chemotherapy or something else. So it can also be applied to a nanoparticle plus hadron therapy. So of course, if you put many things instead of just one thing, you supposedly have a higher outcome. Okay, but it doesn't always mean that it's better.
Okay. Questions? Okay, thanks again to the speaker. The session is ended, but we have to run in front of INRiM, everybody, to make the photo. And then we take the bus to go to the observatory of Pino. Take all your stuff because we don't return in INRiM.